been down somewhere. Looking at our PV diagram, constant pressure plot looks like that. What's the area underneath?
E times V.
Not V, but
Delta V.
delta V. Yeah, I'm not starting at zero there. It's so my area is P delta V. So my thermal energy, or change in thermal energy, I should say, is equal to QP plus P delta V. Now I'm not going to do it 100% of the time, but I try to separate velocity from volume. I try to put the serifs at the top of the volume, V. I obviously didn't do it as a subscript here, but that's my attempt. And this QP, well, it's over there, so this is equal to NCP delta T plus P delta V. If we assume an ideal gas, so what's the ideal gas law? Chemistry version.
EV equals RT.
So P delta V is equal to, well, if I have a set amount of gas, I'm not changing the number of moles, R is a constant, so that would be NR delta T. So my equation down here becomes so if NC delta T, NCV delta T equals NCP delta T plus, well, P delta V, which is NR delta T. I now have N as a constant in every term. I have delta T in every term. And I'm left with that this value of CV is equal to CP plus R, the gas constant. All right, there's a small mistake here. I forgot my minus sign. So CP minus CV is equal to R. And there is a table on page 362 of your book. Sorry, 632. Page 632, table 21.3, well, there's only one table on it, but they give it for various gases, looking at the difference between the molar specific heat with volume constant versus pressure constant and the differences. And it comes out to about 8.3, as one would expect. All right, let's take it one step further. If I look at the ratio of the two values, so for a particular, just take an argon, just for example, CP is 20.8. So for argon, CP 20.8, and CV is 12.5. And so we get a difference of 8.3, which is in the proper units is gas constant. I guess joules per mole Kelvin. I'm not going to define another value and look at CP over CV, look at the ratio of these two things. I know CP is equal to R plus CV. Which which is R over CV plus 1. Now, this value of CV, we sort of already done that in a sense that we did the derivation relating change in temperature with basically relating temperature and kinetic energy. So if we're dealing with thermal energy, again, it's just kinetic energy. We had that, let's make sure I put things down correctly. 3/2 in R delta T. And we had the 3 there. Originally, we had a 1/2 in there when we were dealing in 1 dimension. We went to 3 dimensions, that's where the 3 pops in. It basically is degrees of freedom. So that comes from the number of degrees of freedom. That will come in handy in just a moment. So setting these equal to each other, N cancels out, delta T cancels out, so we have CV is equal to 3/2 R. So popping that in over here. So this goes R over 3/2 R plus 1, which is 1 2/3, which is about 1.67. If you look at that table there, you'll see that even at these ratios right here, you get the ratio of the pressure constant 1 versus the volume constant 1 to be 1.67. So what we find experimentally seems to match what we derived, which should feel good. If I take a diatomic molecule, so not just a monatomic, just a single, I've got basically a point particle here, I now have some depth to it. I in essence have 5 degrees of freedom. I've got the 3 translational degrees of freedom, and then I can spin around that axis, spin around that axis. That's not really a degree of freedom because there's no difference in the particle spinning like that. So it counts as 5 degrees of freedom. So what I'd expect for a diatomic molecule is CV is equal to 5/2 R, because I have 5 degrees of freedom. So I end up with somewhere around, my gamma value should be somewhere around 1.4, which really seems to match for the diatomic molecules. Except, when you take a diatomic molecule and you get it hot enough, this number changes. It worked great at room temperature here, or even works great at room temperature, but it does not work particularly well at high temperatures. And that was one of the issues that classical physics ran into. There are several issues that classical physics ran into, but that's one of the issues that we run into in classical physics, which doesn't get resolved till quantum physics comes about, which is a Physics 252 topic. There are about 5 major issues with classical mechanics which don't get resolved till quantum mechanics solves them. All right. Questions here? All right, so let's now deal with cycles. Or deal with specific situations. Then we'll get into the cycles. And also, everyone's favorite, vocabulary. Adiabatic process. These are special cases that we're dealing with. We will be constantly going back to the PV diagram. In an adiabatic process, there's no energy exchange because of difference in temperature. So my change in thermal energy is just solely the work done on the system. Manipulating this around a little bit because I'm going to come up with stuff that we'll use later. If, put it in terms of differential here, dW, and this W is for work, is equal to negative PdV. And if we're assuming ideal gas, I know that P is equal to nRT over V dV. Make sure I want to be using that version of it. Yes, I do. That's equal to the work, I guess, dW, which would also be equal to, oh, just did that. NCV dt, or delta t, but start looking at the differential in CV dt. N's going to cancel out. And I'll leave R in for now. Working this around, getting all the variables, getting the volumes on one side and the temperatures on the other. I've got negative R over CV times dV over V is equal to dt over T. This R over CV, well, I know that's CV minus CV over CV, which is CP over CV minus 1, which, as we defined gamma over there, gamma minus 1. So my equation right here then becomes negative gamma minus 1 dV over V is equal to dt over T. Let's do some integration. Actually, do I need to do the integration? Yes, I do. Do the integration, we get negative, actually, let's go ahead and flip that around. 1 minus gamma natural log of V from some initial volume to some final volume is equal to the integral of the not the integral, done that already. The natural log of the temperature for some initial temperature to some final temperature. So we have 1 minus gamma times the natural log of Vf over Vi equals the natural log of Tf over Ti. Now, I did make an assumption about your background with logarithms. Everyone comfortable with subtraction being the same as division here?
Yeah.
Okay. So that's the same as the natural log of VF over VI to the 1 minus gamma equals the natural log of T F over Ti. And do the inverse function for both, or this must be equal to that. We have VF over VI. Okay. 1 minus gamma is equal to TF over TI. Taking it one step further, again, assuming ideal gas and a PV equals nRT. So temperature here is just some constant times PV. So if we, so 1 over nR PV final. So adiabatic 1 over nR V initial V initial. This over here is just VF, so that, well, that cancels out. That's going to be equal to VF over VI times VF over VI to the negative gamma. VF over VI cancels out. I'm left with my final pressure over my initial pressure is equal to my final volume over my initial volume to the negative gamma, which is just my initial volume over my final volume to the gamma. Cross multiplying there, I get P final times my final volume to the gamma is equal to P initial volume initial to the gamma. In essence, this relationship here is that PV to the ratio of CP to CV is a constant for adiabatic relationships, for an adiabatic process. In other words, there's no heat, no energy exchange because of difference in temperature. I know it's a lot of, it's basically alphabet soup on the board. However, questions? All right, we'll tuck that away, that's gonna come back. Got it. All right, special process number 2, isothermal. So what does isothermal mean?
The temperature stays the same.
Yep, no change in temperature. For whatever reason in my notes, I switched it to the physics version of ideal gas law. So it's equal to 0, so my thermal energy is not going to change. And so I'm left with therefore 0 is equal to Q plus W. Or W equals negative Q, which is negative integral of PdV. I'll stick with my notes. I know that PV is equal to nRT or equal to n case of dt. In case of bt over v dv. Temperature's not changing, so obviously, therefore, temperature's the constant, it can come out. In kBT, integral of the negative dV over V. Get that fun little natural log showing up yet again. And when I first was introduced to natural logs in whatever, algebra 2, algebra whatever it was, did not realize how often it actually shows up. It's as if the math people teach it for a reason. Of V final over V initial. And we can get rid of the negative sign by bringing it here, raising this to the -1 power, and so we get n kBT, natural log of V initial over V final. Yeah, it is that exciting. Again, alphabet soup. It will come back and haunt us later. Part of this is one, we're going to be dealing with PV diagrams where